Thank you very much for this presentation. We're going to move on to a new session. We'll have the presentation by Gérard Moreau to talk about the contributions of Edmond Becquerel in photovoltaics. I'm going to hand the floor to Jean-Éric Bourret and Jim Slines, who will be the facilitators. Jean-Éric, over to you.
Thank you very much, Alexandre. So I have the pleasure with Professor Jim Slines from Colorado State University to co-chair the photovoltaic session. Professor Slines has received the last IEEE William Sherry Award. I will present the first speaker, Dr. Jérôme Fatet, and Professor Slines will present the second speaker, Dr. Daniel Linko. My name is Jean-Éric Bourret. I am a retired researcher of CNRS. Since 1976, I have been working in various French laboratories for several types of semiconductors of solar cells. First on gallium aluminum arsenide heterostructures for splice applications, then on upgraded metallurgical grade polycrystalline silicon with the late Michel Rodot, then at École Polytechnique on amorphous and nanocrystalline silicon, and finally on hybrid perovskites. This afternoon, we will have a speech of Professor Snaith about the subtle perovskites, which are mixed conductors. Now I am presenting to you Dr. Jérôme Fatet, a professor at the University of Limoges, with the author of a thesis in history and philosophy of science. And this thesis was entitled Edmond Becquerel Research on the nature of the light between 1839 and 1843. This corresponds exactly to the study of the electrochemical effect due to sunlight, which was the title of the original report of Edmond Becquerel, presented in November 1839. Professor Fatet, I give you the floor.
Est-ce que vous m'entendez?
Un peu plus.
Je ne sais pas si vous m'entendez.
Plus fort. Plus fort. Plus fort.
Bonjour, est-ce que vous m'entendez?
Oui, vous pouvez mettre un peu plus fort, s'il vous plaît.
Un peu plus fort. Je peux essayer de mettre un peu plus fort.
De parler plus fort pour l'interprète.
Ok, alors je vais...
On n'entend pas bien.
Non, on l'entend.
C'est bon, mais il faut parler plus fort.
Oui, il faut parler plus fort si c'est possible.
Alors, je vais essayer de parler plus fort. Est-ce que c'est mieux?
Oui, beaucoup mieux, beaucoup mieux. Merci
Très
beaucoup.
bien. Alors, je vais essayer. Très bien. Alors, est-ce que le partage fonctionne?
Can you see my presentation? Thank you. Hello, everybody. Today, I'm going to present to you the work that Christine Blondel talked about in the first part of this session. Edmond Becquerel's work on the development of the electrochemical actinometer and the discovery of photovoltaic effect. His work started in 1839. He was 18. It was the year of the publication of the first photographic process by Daguerre, which was named the daguerreotype. Edmond Becquerel was extremely interested in this photographic process. And under the influence of Argot, Edmond Becquerel starts working in research on his thesis on chemicals, an analysis of chemical reactions on the effect under the effect of solar light. And he carried out many photographs, like this photograph of the Tuileries Gardens that was done in daguerreotype in 1840. It has two competencies, a technical competency, a skill in photography, and he worked as a scientist, as an assistant of his father at the Natural History Museum. In 1839, there was controversy on light. There was a certain amount of consensus, but the debate was going on. There were the defenders of the wave theory. Gustave Fresnel, for instance, defended this theory that was widespread. And there were the defenders of the corpuscular theory of light, the Newtonian theory. The defenders were few in number. And one of the central figures concerning the work I'm presenting to you is Jean-Baptiste Biot in 1839. He was one of the most fervent partisans of the corpuscular theory of the nature of light. The nature of solar radiation was discussed. There were three different spectra that were distinguished, that were identified. So the heat rays that were identified by Herschel in 1800, the light rays that produce light, heat rays give off heat, light rays, and chemical rays that provoke photochemical reactions. There is a fourth spectrum of radiation at the time that was explored by César Becquerel and Jean-Baptiste Biot. And these are phosphorogenic rays that produce phosphorescence. So solar light at that time has these four spectra of radiation that are identified as having different characteristics and that are partially superimposed. The difference bears, as far as chemical rays that we're going to talk about, different because we give to each spectrum according to the theory, depending on the theory that you use. In the corpuscular model, light rays are accompanied by conjugate elements, and it's these elements that produce chemical effects. And this is what Jean-Baptiste Biot believed. And the number of causes, the diversity of these congeneric elements and the respective effects of each are inaccessible to experimentation. They accompany light, but they are not quantifiable, cannot be experimented on. The wave model, only chemical rays generate chemical effects, and it is possible to envisage studying these chemical rays by looking at the effects on materials. And from 1939, Becquerel positions his research according to the wave theory, as he starts to study photochemical effects. But he doesn't put forward any theories. He is very cautious as far as a theory is concerned at that point in time. In 1939, he proposes the creation or building of a first device. It's a completely opaque vase which has two liquids, the difference, which are superimposed very delicately, one over the other. And in each of the liquids, there's a substance that is dissolved that's going to react under the effect of light with the substance of the other liquid. And the reaction can only be produced at the interface of the two liquids when it is exposed to light. In each of the liquids, there is a platinum electrode, which is connected to a galvanometer. The idea is when light hits the interface, a photochemical reaction may take place, which will be able to be proven by movement of the needle of the galvanometer. He conducts these first experiments, he measures the first effects, and from the first publication on this topic, Jean-Baptiste Biot is going to react and challenge him. And Becquerel's approach is as follows. He says that the quantity of rays that will be, or radiation, is proportional to the quantity of the substance that reacts to the interface. And that this quantity of substance is proportional to the maximum deviation of the galvanometer, therefore the current that can be measured. So by measuring the current, he'll be able to evaluate the amount of radiation that is received and studied therefore, and this chemical effect. This part, the lower part of this reasoning, was proven by César Becquerel a few years before, and he got the Copley Medal for this. The upper part of this assumption is a hypothesis of Becquerel, which is the first apparition of the what he calls later the photovoltaic effect, the production of electric current by light. Now, there's controversy starts, and it's based basically on experimental aspects. Becquerel has to take this into account, and it enables him to develop his experiments further. But in fact, there is a disagreement as to the proportionality between the quantity of light and the quantity of substance that reacts. So a disagreement that seems to be based on theoretical differences. This opposition on the part of Biot is irrelevant because Jean-Baptiste Biot says to Becquerel that in fact there is no certainty as to that the electric effects that he measures with the galvanometer are due only to the chemical reactions. There could be other effects due to the light directly on the platinum electrode. So light on the metal that would add up to the effects measured during the reaction, the exposure to light, which render it impossible to quantify the effect. We wouldn't know what the share of the effect is due to the photochemical effect or to the direct effect of light on the metal connections. So if Becquerel wants to be able to validate his results, he has to address this challenge. So he's going to invent a new type of device that I call a two-compartment or dual compartment device. And here you have an example. This is a replica that I built, which contains two compartments. It is a wooden oak box filled with liquid that contains two compartments which are separated. But the intermediary partition does go all the way to the bottom. So it means the liquid can circulate between the two compartments. So the wooden box is filled with water that's spiked with acid. And in each compartment, we put a platinum plate, which reproduces the parts in the initial experiment. So you can light one of the two plates from the front, the other one remaining in the dark. And the idea here is if the light acts directly on the platinum electrodes, it's only going to have an effect on one of the electrodes. These two plates are connected to the galvanometer. And if there is an effect of light on one side, you can note a disbalance or disequilibrium, and you can therefore say whether light is having a direct effect on the metal or on the plates. This result was to be published. The results published at that time show that he is measuring the effects of light on the platinum plates when he heat them and take away the film on them, it will be no longer an effect. So he was able to prove that his first experiment was valid, and therefore is going to do something extremely important. Since he has obtained results that are measurable with platinum layers, plates covered with a layer of, he's going to do the same thing with metal plates that he's going to use in daguerreotype with a thin layer of photosensitive material. And from that moment on, he's going to start to use inside his reservoir plates prepared in the same way as photo plates. So plates of silver with silver chloride layer on them and expose one of the two plates to light, and the other one will remain in the darkness. So then we see complete reversal in the focus of his study. At the time, he wanted to look at the reactivity of photosensitive substances to solar radiation to see what effects could be measurable. And from that moment on, he's going to start studying sun radiation through photosensitive substances have fixed and chosen, generally silver chloride, enable him to measure the different parts of, or sections or spectrums of solar light. For the first time appears the use of the electrochemical actinometer. That it makes it possible to measure light activity. So the electrochemical actinometer makes it possible to measure the activity of light through electromechanical reactions. So here you have the device, you have the receptacle in which two plates are immersed. This graph shows all the different parts. It doesn't look exactly like this, but each of these plates is connected to a galvanometer with a long connectors. I'm going to present it's not quite the same device as one used by Becquerel. This is one that exists from pretty much the same time. So galvanometer, you have wire that's wound, and the coil, over the coil you have a needle which is magnetic, and it's going to move according to the electric current in the coil. The disc, which is here, we're talking maximum deviation of the needle of the galvanometer with degrees from 0 to 90 degrees that can be measured. You can look at the degree of deviation. It's measured in microamps. And here the coil that we have dates from back to the time 800 tours. It's the galvanometer used by Edmond Becquerel between 24 and 30,000 revolutions, which gives it a sensitivity of 10 microamps or even a microamp. So extremely detailed, extremely sensitive measuring device. So the idea is to send the light through this hole on a screen that is going through a prism, is going to decompose the solar light with this prism and send successively different parts of the solar spectra to be able to analyze the different effects successively of each of these spectrums. And it's going to measure more and more detail the light rays to measure the different parts of the solar spectrum. And it means he's going to deviate the spectrum so as to send the different parts of the spectrum. In 1841, he announces that he's proven, at a certain moment, he observes for certain tiny areas of the spectrum that there is no electric effect. So deduces from there's no light. So he's going to draw black lines where there's no light. And he's going to identify 300 dark rays in the chemical and light spectrum. And these dark rays are superimposed by the ones identified by Fraunhofer a few years before by using the eye as a detector. What it means, therefore, is that we've identified properties. They're dark rays at exactly the same places, and there's a perfect superposition between the two experiments. There's therefore identical properties between the light spectrum and the chemical spectrum, and that will enable him to continue his study. And at that time, he's going to continue to displace the spectrum over and beyond ultraviolet. It's going to go out into the ultraviolet. And he's going to measure electrical effects based on the ultraviolet zone. And in 1843 announces that he has measured 3 dark rays beyond violet, the ultraviolets exist, and what proves this are the rays that you find in this part of the spectrum. So we've the identity properties between what there was before violet and what was after the violet. We have dark rays, and we have a juxtaposition of the zones because experimentally he simply starts to displace the spectrum beyond the violet, and he deduces that there's the same nature between what is before violet and what is beyond violet. And he's going to widen the definition of what we'll be able to call light. And he wrote in 1843, I use the names of light rays, chemical phosphogenic rays, to designate what are the portion of solar rays and what a portion of chemical phosphogenic rays. And I deduced that's the same radiation. So it means he proves that it would be possible to unify the 4 types of rays that I talked about earlier on under the same description or nature. It's light that's going to provoke different types of effects. It's the same light. During this time, Jean-Baptiste Biot challenged what Edmond Becquerel was saying, but from the moment that he identified dark rays within the ultraviolets, he's going to start pursue his work further in a field which seems to be a completely different theoretical field, although he never takes any firm position regarding this. We have the theoretical position that he stated at that time. I just have one word to say in conclusion. So all the experiments Edmond Becquerel conducted at that time with the different devices, I looked at these, and I have insisted on what Christine Blondel said earlier on the extreme experimental precision and detail. These are experimental works that are remarkable. The electrochemical actinometer will continue to be used in different laboratory experiments in the second part of the 19th century and become, amongst photographers at the time, electrochemical sensitivity measuring device to be able to measure the sensitivity of the photographic plates and be used uses. Another important thing to evoke and to highlight is one of the questions that raised: why did Edmond Becquerel, why was it difficult to pay homage to his discoveries? Probably because the results were very quickly taken on board by the scientific community. And under 3 years, as from 1846, there were a number of chemical treatises that quote or cite these discoveries as important discoveries. Edmond Becquerel was 22 years old, and he was probably too young to hope to have attributed to him this research work. So this due also to the speed at which scientific community absorbs this information, and this may be a reason why his name was not, or these discoveries weren't attributed to his name. And so this is an important part of the work that Edmond Becquerel did to discover the photovoltaic effects. And we will have further details presented concerning this discovery in the morning. Thank you very much for your attention.
Thanks, Professor Fatet, for this very clear and enthusiastic talk. We have one question from the audience. This question is, so I turn in French.
Mr. Fatet, what other method did we have at the time to measure the intensity of light? That's an excellent question. We had very few methods to evaluate the intensity of light. As far as I know, whatever the systems used, the final detector was the human eye. That is to say that among all the devices, optical devices used, even for phonophore, was developed with a very precise optical device, but the final detector is the human eye for the intensity of light. I believe the electrochemical actinometer is the first tool, I use the term tool, that makes it possible to have objective data, which will make it possible to compare the results over and beyond the sensitivity of each individual experimenter. Thank you. There is a second question. You talked a great about the actinometer and the galvanometer. So we're measuring different intensities. Could we measure tension? Voltage. It wasn't at all the objective with this experiment. We're really focusing on the intensity. One of the big specialists is Christine Blondel, and the further discussions, we have to hand the floor to her and ask her about this. Here, in fact, in reality, what was the deviation, the electrical effects, but we weren't talking about the voltage, measuring the voltage, in fact. No, we didn't go all the way to infrareds. There were other researchers that worked on the infrared. Thank you very much, Professor Fatet, for your wonderful presentation. Now, I'm going to go back into English.
Now I give the floor to Professor Seitz from Colorado State University to present the second speaker, who will be Dr. Daniel Danko.